Hello everyone, hope you guys has watched the previous recording about the redox reactions and how to balance them. So in this section we're going to talk about electrochemical cells. There are two types. One is called a voltaic cell, another one is an electrolytic cell. In a voltaic cell it uses spontaneous redox reactions, meaning delta G going to be less than 0 to generate electrical energy. Okay, so in this case the system does the work on the surroundings. Remember, we learned about the spontaneous reactions in our previous chapter about thermodynamics, that for a spontaneous reaction delta G need to be less than 0, negative. That's a voltaic cell. And if you take electrolytic cell, it uses electrical energy to drive a non-spontaneous reaction. So the electrolytic cell is non-spontaneous. It uses electrical energy. Non-spontaneous meaning delta G is going to be greater than system. So in this case, the surrounding does work on the system. Okay. Both types of cell are constructed using two electrodes placed in an electrolyte solution. There are some terms that we are going to learn: anode and the cathode. Anode is the electrode at which oxidation occurs. Remember, in a redox reaction, there are two parts: oxidation and reduction. These are going to be in two separate containers. So, anode is the electrode where the oxidation occurs. We call the cathode for the electrode at which the reduction occurs. Okay, anode is the oxidation and cathode is where the reduction takes place. And here's characteristics of a voltaic and electrolytic cell. So what's the difference between the voltaic cell and electrolytic cell? Voltaic cell, it's a spontaneous reaction, delta G less than 0. Electrolytic cell, non-spontaneous, surrounding has to do the work, delta G greater than 0. Okay, so this is a voltaic cell. Energy is released from a spontaneous redox reaction. And system does work on the surrounding. System does the work. So here you have two solutions containing electrolytes, and also you have anode and the cathode. Anode is where the oxidation takes place. Cathode is where the reduction takes place. Okay, anode, cathode. And this is the surroundings. They are connected. So the electron flow where the oxidation happens to the reduction electrode. Oxidation is releasing electrons, so those electrons gonna go through and come to the cathode where the reduction take place. Oxidation half reaction, you lose electrons. Reduction half reaction, electrons will be taken up by the cathode and then reduced. So for the overall reaction would be X plus Y plus, giving you X plus and Y. Delta G going to be less than 0, which is spontaneous. And in an electrolytic cell, energy is absorbed to drive a non-spontaneous redox reaction. Surroundings, there should be a power supply to do the work on the system, which is a cell. Again, you have the electrolyte with A minus and B plus electrolyte, cation and the anion. Anode here is oxidation takes place, and cathode is where the reduction takes place. So from the power supply, you have to supply energy. Okay. Oxidation half reaction would be A minus becoming A by releasing an electron. And reduction half reaction, electrons will be taken up and then will be reduced. So this is the overall reaction, delta G greater than 0. Non-spontaneous reaction. Both of these setups are somewhat similar, but the difference is for the voltaic cell, it's a spontaneous reaction. System is doing the work, whereas electrolytic cell, which is non-spontaneous reaction, delta G greater than 0, surrounding has to do the work in order for cell to work. Okay. So in a spontaneous redox reaction, so let's see what's happening. A strip of zinc metal in a solution of copper ions will react spontaneously. So we have copper and zinc. Copper 2 plus, let's say copper nitrate, takes up electrons and become copper solid. This is the reduction. And the 2 electrons that is being lost going to taken up by zinc. The copper is going to take 2 electrons and become copper solid. I said something wrong in the previous line. Okay. So the 2 electrons, so where does the copper gets these 2 electrons? It gets from the zinc. Zinc is losing 2 electrons. Okay, zinc is where the oxidation takes place. Zinc loses 2 electrons and becomes zinc 2 plus 2 electrons. So the overall reaction would be copper ions plus zinc solid becoming zinc 2 plus and copper solid. Zinc is oxidized and loses electrons to copper. Oxidized gives its electron to copper. Although electrons are being transferred, electrical energy is not generated because the reacting substances are in the same container. If we put zinc and copper both in the same container, there is a spontaneous redox reaction, but the energy is not generated since they are in the same container. So, here's a picture diagram of a spontaneous reaction between zinc and copper ion. So zinc is a solid. So zinc is this strip. Zinc strip, and this blue color solution is copper nitrate. Zinc is being oxidized. Zinc is giving 2 electrons. So zinc will become zinc 2 plus. The 2 electrons that is being lost will be taken up by copper 2 plus, and copper solid is deposited as a solid. So if you keep it for some time, copper is a metal, you can see copper nitrate. This solution is copper nitrate. That the copper 2 plus ions are being converted to copper. So this additional solid that is being formed, that is the copper metal. What happened to the color of the solution? This is dark blue and this is more lighter. This is copper nitrate. As the copper ions being lost from the solution, the color of the copper nitrate become lessened or reduced. Okay. So visually you can see that the zinc metal is being oxidized. And here one more thing that you can notice is, since zinc solid is being oxidized, it becomes zinc 2 plus. So can you see that the zinc trip is being also reduced here? You see here it becoming smaller, kind of reduced, whereas the copper metal is being formed, and then the copper ions from the solution being expelled to make copper solid. So zinc become less, copper will form more copper. Okay, when I say zinc become less, which is a zinc solid or this strip over here. Construction of a Voltaic cell. Each half reaction take place in its own half cell so that the reactions are physically separate. So we're going to construct a Voltaic cell. We are going to keep the 2 half reactions, which is your reduction and your oxidation, in 2 separate containers. Each half cell consists of an electrode in an electrolyte solution. We need an electrode, which is a piece of a metal, and the electrolyte solution that contains the same metal. The half cells are connected by the external circuit, and then we also put a salt bridge to complete the electrical circuit. Let's look at all these components in this diagram, and this is a Voltaic cell based on the zinc copper reaction. In this diagram, you are seeing zinc and the copper, both of the reactions, like both of your half reactions, are in the same container. Now we are going to separate them. Over here, they have been separated. You have a zinc strip in a zinc solution, and you have a copper electrode in a copper solution. Wherever the oxidation takes place, that's your anode. Wherever the reduction takes place, that's going to be your cathode. Okay? And they have been connected by a voltmeter. So zinc is being oxidized. So electrons are going to move through the wire and come to the copper electrode. And then the copper will be reduced over here. And there is a salt bridge. Salt bridge help to balance the ions in the both solutions. You have sodium ions and sulfate ion. It need to be a cation and an anion. Okay. So what is happening in the anode? Oxidation half reaction. Zinc solid becoming zinc 2 plus and releases 2 electrons. And then the reduction half reaction, copper ions takes up 2 electrons that is being lost from the zinc and become copper solid. And this is the overall cell reaction. When you add these two together, 2 electrons will get cancelled. Zinc plus copper becoming zinc 2 plus and copper solid. Okay. Operation of the Voltaic cell. Oxidation, which is a loss of electrons, occurs at the anode, which is therefore the source of electron. Right? That is why it is negatively charged. Anode is negative sign and the cathode is positive sign. Negative means it has electrons in it. Okay. Over time, what happened to the zinc is zinc anode decreases in mass and the zinc ions in the electrolyte solution increases. Reduction, which is the gain of electrons, occurs at the cathode, where the electrons are used up. So copper ions in the solution takes up 2 electrons and become copper solid. So what happened to the mass of the copper strip? It will increase. Over time, the copper ions in this half cell decreases and then the mass of the copper cathode increases, which is the solid copper piece. Like this. So if you keep it after several hours, you can see zinc anode would weigh less and then the copper cathode weighs more. Charges of the electrodes. So zinc plus copper 2 plus giving you zinc ions and copper is the overall reaction. The anode produces electrons by the oxidation of zinc. The anode is the negative electrode in a Voltaic cell. Negative means it is dense in electrons. Electrons flow through the external wire from the anode to the cathode, where they are used to reduce copper 2 plus ions. So the cathode is therefore the positive electrode in a Voltaic cell. And remember, there is a salt bridge. What does the salt bridge do? Over here, this is called the salt bridge. It has a positive ion and a negative ion, sodium ions and sulfate ion. Let's look at what it does. The salt bridge, it completes the electrical circuit and allows ions to flow through both half cells. As zinc oxidized at the anode, zinc 2 plus ions are formed and enter the solution. You have a zinc metal strip, it oxidizes and becomes zinc 2 plus. It comes to the solution. Copper 2 plus ions, it leaves solution to be reduced at the cathode. So the copper 2 plus ions that was in the solution becoming now copper. The salt bridge maintains electrical neutralite by allowing excess zinc ions to enter from the anode and excess negative ions to enter from the cathode. So the salt bridge contains non-reacting cations and anions, often potassium ions and nitrate, dissolved in a gel. So for example, pen, look, I'm trying to get my pen. Okay, there you go. So what is happening? There is a zinc strip. Zinc becoming zinc 2 plus. Right? So zinc 2 plus enter into the solution. So then in our original solution you have a cation. So there need to be an anion to neutralize it. So when from the salt bridge, if you have K plus and nitrate ions, from the salt bridge helps to have a counter ion for these nitrate zinc ions. Okay. Similarly for the copper 2 plus ions plus 2 electrons become copper. So it loses copper ions from the copper solution. So the potassium ion will come to replace the lost copper ions from the solution. So the salt bridge helps to maintain ionic balance in the solution. Salt bridge contains non-reacting cations and anions, often potassium and nitrate, dissolved in a gel. Flow of charge in a voltaic cell. Electrons flow through the wire from anode to the cathode. Anode is where the oxidation takes place. Zinc becoming zinc 2 plus and 2 electrons. Cations move through the salt bridge from the anode solution to the cathode solution. Cations move through the salt bridge from the anode solution to the cathode solution. Anions move through the salt bridge from the cathode solution to the anode solution. Just like I explained in the previous slide, to balance the electrolytes in the two solutions. By convention, a voltaic cell is shown with the anode on the left and the cathode on the right. Active and inactive electrodes. Active electrode is an active component in its half cell and is a reactant or product in the overall reaction. Just like what we had talked so far, zinc electrode, copper electrode, they are active. They are actually participating in our redox reaction. An inactive electrode provides a surface for the reaction and completes the circuit. It does not participate actively in the overall reaction. Inactive electrodes are necessary when none of the components can be used as an electrode. Now, if it is a metal that involved in the oxidation reduction reaction, we can use an electrode. But sometimes, for example, if you are using a gas like hydrogen, we cannot have a hydrogen piece or a hydrogen solid, right? So in that case, we would use an inactive electrode, providing a component to use as an electrode. Inactive electrodes are usually unreactive substances such as graphite or platinum. Graphite is carbon. We use carbon or platinum as inactive electrodes. So here's an example where we can use inactive electrode. Here we have a carbon or graphite electrode. And this one also carbon graphite electrode. Oxidation reduction reaction happens between iodine and potassium permanganate. So both of these we cannot have metals. So iodine is a solid right here, this purple color stuff. but you cannot have a strip like this iodine strip. So in the oxidation half reaction, 2 iodide becoming iodine and losing 2 electrons, and then the manganate takes up electrons to become manganese ion. And this is the overall reaction. So this is an example where when we are constructing a voltaic cell using inactive electrode, and our inactive electrode in both cases is carbon, C for carbon, anode and the cathode. We need to know how we can express this voltaic cell. So there is a cell notation. The components of each half cell are written in the same order as in their half reactions. The anode components are always written on the left anode where the oxidation takes place. First you write how it is happening. Zinc is becoming zinc 2 plus. You also have to express what is the phase state of the materials. For example, zinc is a solid. So you want to express zinc is in the form of solid. And then this line tells us that they both are two different physical states. This is solid and this is aqueous. Anode components are written on the left. Cathode components are written on the right. They are written in the same order as in their half reactions. The single line shows a phase boundary. This line, phase boundary between the components of a half cell. Phase boundary, phase boundary. The double line over here shows that the half cells are physically separated. This tells they are physically separated in two beakers. If needed, concentrations of dissolved components are given in parentheses. If not stated, it is assumed that they are 1 molar solution. So zinc solid becoming zinc 2 plus aqueous, double line, they are physically separated. In the cathode, what's happening? Copper 2 plus ions becoming copper solid. Okay, and this is how you normally write a notation for a voltaic cell. Another example where you would use inactive electrode. For example, our iodide and permanganate example. Graphite is the anode. So you write the anode first. Physically separate, not physically, the two phases, different phases. You can put the line here. And then what is happening? Iodide, aqueous becoming iodine solid. That's what's the oxidation. And then the two cells are physically separated, two lines. And in the anode, not anode, cathode, where the reduction takes place, what's happening? Permanganate, aqueous solution with hydrogen acidic medium becoming Mn2 plus aqueous. This is all your reduction. And then it is happening on graphite electrode. Inert or the inactive electrode is specified graphite. A comma is used to show components that are in the same phase. So this comma, it means they are in the same phase. If they are not in the same phase, we have to put a single line. Graphite is a solid, aqueous, solid. Here they are in the same aqueous medium. So we just put a comma to separate them. Okay. Draw a diagram, show balanced equations, and write the notation for a voltaic cell that consists of one half cell with a chromium bar in a chromium nitrate solution. So one is chromium in chromium nitrate. Another half cell with silver bar in silver nitrate solution. And you have a potassium nitrate salt bridge. Measurement indicates that the chromium electrode is negative relative to the silver electrode. Now we are given two solutions with electrodes in it. We also given a very important piece of information. It says chromium electrode is negative. relative to silver. What does that mean if chromium is negative? Which one is the negative electrode? Is it the anode or the cathode? Anode, right? Negative electrode. So chromium electrode, if it is negative, that's going to be your anode. So that means that is where the oxidation takes place. So then the silver bar should be your cathode, where the reduction takes place. So we can write the half reactions. Chromium becoming chromium 3 plus, taking 3 electrons, which is the oxidation. Silver ions then take up electrons and become silver solid. That is where the reduction takes place at the cathode. So how do you know it's chromium 3 plus? Remember, it's going from chromium to chromium nitrate. Nitrate charge is -1. So since the formula is given, nitrate is -1, there are 3 of those, -3, so the chromium needs to be chromium plus 3. So chromium becoming chromium plus 3. So this is your oxidation. So for the reduction then, silver ions taking electron become silver. Reduction. 1 electron plus 3 electron here, loses 3 electrons. So to make it equal, you have to multiply this by 3. That would make it 3 silver plus 3 electron, 3 silver plus 3 Ag solid. When we add the two together, the 3 electrons to 3 electrons cancel, and we have this overall reaction: 3 silver ions plus chromium, 3 silver and chromium 3 plus. That's the overall balanced equation. And this is the cell. Chromium strip in chromium 3 plus solution. That's the anode, negative electrode. And then the cathode, you have a silver strip in a silver ion solution. And then the electron flow from chromium to silver cathode. Anode, cathode. And this is the salt bridge. Since chromium is becoming chromium 3 plus, more cations from the salt bridge, nitrate ion comes to this side to balance the chromium 3 plus with nitrate ions. And from the cathode, silver ions will become silver. So it loses the positive ion. So from the salt bridge, positive ions move to the solution to balance that. And this is the cell notation. You first write your anode, what's happening: chromium solid, phase change, becoming chromium 3 plus aqueous, physically separated 2 bars, silver ions aqueous, becoming silver solid. This is a solid, this is aqueous, so you have a bar to separate them, 1 bar. The cell diagram shows the anode on the left and the cathode on the right. Okay. Okay, so probably we'll stop here and then